So imagine we have the hypothesis, the necessity hypothesis, like the types you have formulated. And how do we do the data analysis, the necessary condition analysis? 4 steps. First, you formulate the hypothesis with an x and a y. You can have several hypotheses, of course, but let's say we have one. Then you do the measurement, you collect the data. Valid, reliable data. Not different for regression or not different for necessary condition analysis, just good data. Good data for the x, good scores, and good scores for the y. And we had a discussion on this table about measurement. It's not a part of necessity thinking that it must be different type of measurement. No, the measurement must be just good measurement, valid and reliable. So we need good data. You analyze the data in a different way. I come back to that. That's the core difference of necessary condition analysis. First of all, the hypothesis is different, and second of all, the data analysis is different. And then you report yourself. That's basically what you do. So this is an important characteristic, parsimony, we call it simple models. Science goal is to summarize reality somehow in simple ways, in models, in approximations of reality. And parsimony is a big goal of science. So this necessary is extremely simple. 1 x and 1 y. And I think that is maybe an underestimated value of necessary condition analysis. So we are going into structural equation modeling, more the better. And I think in the end that's not good because it's not practically useful. So because it can be simple, and therefore it can only be a bivariate analysis. So only 1 x or 1 y. We don't need the other x's. And it is, if you have more necessary conditions for a certain y, you do a separate analysis for each condition because they don't depend on each other. And this is so nice that you, in a multivariate necessary condition analysis, you don't need all the variables, but in a normal analysis you need all the variables and the control factors to do multiple regression or structural equation modeling, etc. So it can be very simple, and this is the simple x and y analysis. It's based on just a scatter plot. I have my cases, I have an x, I have the y, and we until now talked only about dichotomous variables, absent or present, low or high. So this, what I call, is the dichotomous necessary condition. So what we said, so if x is absent, there can be only one outcome, the y is absent. It's impossible to have with an absent x a present y. But if the x is present, you have two opportunities, two possibilities. The y can be absent and the y can be present. It's necessary, but not sufficient. This is what you see also in conditional logic, in logic in psychology,
politicality.
No, philosophy. In philosophy you see a lot of these type of reasonings. So it is dichotomous. What I have done is I extended it to discrete variables. So variables that can have 3 levels or 5 levels or 10 levels or whatever. And then you can formulate more necessary conditions in the xy plot. So for having a high level of y, in this example, you must have a high level of x. But for a medium level of y, you need to have a medium level of x. But if you have a medium level of x, you can have a low level of y or a high level of y, a medium level of y.
So the possible range, I guess?
Yeah, this is exactly.
So the dots are...
Dots are cases.
Yeah, that's the cases in order to confirm your hypothesis. And if you have a case in the top corner,
it's not necessary.
You need to
reject.
Exactly, you reject your hypothesis. If you do an observation, you find this data pattern, it corresponds to the hypothesis. To say it more precisely, you did not falsify the necessary condition, because that's what we are trying to do. We try to falsify them. But if you find a observation here. Apparently, it's possible to have the outcome without the x, so it's not necessary. If you extend that to the continuous variables, then you have the continuous necessary condition. And this is the line, what we call the ceiling line. For a certain level of y, if you want to have that, you need to have that level of x. But if you have that level of x, it's possible to have all kinds of values below that maximum value. So basically what we are doing here is we are looking at the empty spaces. That's the essential thing. It's strange, because normally when you look at data, you look where are the data. But necessary condition, where it's empty, where there are no data. That's a fundamental difference. Because you predict absence. So where it's absent, that's the area where it's absent. Normally, when people see this kind of scatter plot, triangular, so here are points, then they say there is a problem of heteroscedasticity. And we need to throw away the data or to transform the data. It's a problem. And I believe that there are a lot of data somewhere hidden that are like that, have not been analyzed because of the problem in regression analysis. The regression analysis doesn't like heteroscedasticity. You get wrong estimations. But it is a characteristic of necessary but not sufficient causality. So we look at the empty spaces. Dichotomous, discrete, or continuous necessary condition. And combinations are possible as well. This is the dichotomous one, discrete one, and the continuous one, but you can also have dichotomous on the x and discrete on the y, or dichotomous on the x and continuous on the y. So there are all kinds of possibilities, but basically what you're looking for is the empty space. And how do you find an empty space? To draw a line between the empty space and the full space. And that line is called the ceiling line. The ceiling on top of the data. Normally what we do in regressions, we put a line through the middle of the data because it's a central tendency. But we put a blanket on the data, a line on the data. We put it on top of the data because above it there's nothing and we are there interested in nothing. That part we are interested in. So we need to draw the ceiling lines. And this one is an interesting, it's in the title of my lecture, for qualitative and quantitative research. This one is interested for what I would call qualitative research. And I give an example soon. And this one is interesting for the quantitative research because you have a lot of quantitative values here. And here maybe it is qualitative in the sense is low or high or more or less and things like that. So these are two types of necessary conditions that are typically used in qualitative research or in quantitative research. Yeah?